So in question number 11, a cyclic process ABCA as shown in VT diagram is performed with the constant mass of an ideal gas. Show the process on a PV diagram. Make a note that AB passes through the origin.
It's like this. AB is passing through the origin. So
Right.
first we try to identify all the type of process and if possible give the values to them. So at A, like AB is a straight line which passes through origin. So V equals nRT by P. Since the slope is constant, so V is directly proportional to T.
Right.
So AB is an isobaric process.
Right.
In AC the temperature is constant, so it is an isothermal process.
Correct.
And in CB the volume is constant, so it is an isochoric process.
Right.
We have to find down the PV, we have to draw the PV curve. So what we can say for now is that let's just draw V1 and V2. We can draw V1 and V2 because we know V1 is less than V2. Now note that the pressure at A would be equal to the pressure at B. So since we have P here,
Yeah.
so this would come a straight line like this. We just have to see now that whether AB, the line AB will be above C or below C. Or basically what will the pressure of C as compared to A and B. So let's go on to find that. So at C we get pressure equal to RT1, P equals nRT by V.
Right.
Yeah, P equals nRT by V, and we just take N to be 1 because it is a fixed number and the relative relationship won't change.
Right.
So P is equal to RT1 P at C by V2.
Right.
And pressure at B would be equal to RT2 by V2. Okay. So now we can see something here because this is R by V2.
Right.
But we have got pressures as a function of temperatures, and we also see that T2 is greater than T1. So this implies that the pressure at B would be greater than the pressure at C.
Right.
And we had shown that the pressure at B would be equal to the pressure at A.
Right.
This equals the pressure at A. So now basically we can write it down. This is one pressure, which is pressure at C, which was lower, so we can write it down as RT1 by V2.
Right.
This is the pressure of B, RT2 by V2. Now we can draw the particular curve. Say this is A, this is B
Right.
at V2, and this is C with the lowest temperature. We had seen, I'm sorry, this is B.
Yeah.
So AB would be a straight line because it is a constant pressure process,
Right.
as we see in here. Just a second, now let's just recheck whether what we had drawn is fine. At C we see V2 and V2 is greater than V1, so V2 C should come out here,
Right.
and the process BC is constant volume. We draw this, and only the process AC is left, which is isothermal, whose graph is like this. So we can now tell the cycle. And
Shouldn't it be A to B to C? It is. Okay.
yeah, it is A to B to C to A.
Right. Okay, so we had done what the question has asked us to. We converted a VT graph into a PV graph, revise the process, and we'll move on to the next question now. Now the 12th question again has two parts. Let's look at what the problem says. 1 mole of a monoatomic ideal gas is taken through the cycle shown. AB and CD are adiabatic paths. Pressure at A is PA and the temperature is TA, which is 1000 kelvins. The pressure at B is PB and the temperature at the same point is TB. You're given the ratio of PB and PA, which is 2 by 3, and then 3 times pressure at C is equal to pressure at A. The first part of the question is you have to find the work done in A to B. Prasoon.
So for finding the work done, let's just see. This is AB is an adiabatic process,
Right.
and for an adiabatic process, we have the formula for work done as work done in an adiabatic process equals to R divided by 1 minus gamma T final minus T initial. So basically, if we are able to find the particular temperatures, then we can find the work done very easily.
Correct.
Now for an adiabatic process, we also know that PV to the power gamma is constant.
Right.
So basically, we have to play along with these formulas to get the particular values. So let's see how these manipulations are done. We have PV to the power gamma constant. V equals RT by P.
Yeah.
So we have P into RT by P to the power gamma equals constant.
Right.
P to the power 1 minus gamma whole into T to the power gamma would be constant. Now this would be the same at A and same at B, because AB is an adiabatic process.
Right.
Hence we start off PA to the power 1 minus gamma dot TA to the power gamma would equal to PB to the power 1 minus gamma whole into TB to the power gamma.
Right.
So we get basically TB by TA equals to, as a function of PB by PA, which is or PA by PB.
Right.
PA by PB 1 minus gamma whole divided by gamma.
Right.
So TB comes out to be 1000 into just placing these values.
Right.
3 by 2 minus 2 by 5. 1000 2 by 3 power 2 by 5.
Right.
And this would be 850 Kelvin.
Okay.
Now we see the work done. Work done was R by 1 minus gamma whole into TB minus TA,
Right.
which is equal to 8.31 by 1 minus 5 by 3 whole into 850 minus 1000.
Right.
After doing the calculation, it would come out to be 1869.75 joules. So
Okay, so we have solved the first part of the problem. Now let's see what the second part of the problem is.
yeah, we have to find the heat lost in B to C. We would have seen the B to C. The process B to C is isochoric.
Right.
So basically PV equals nRT. If this is constant, then P by T would also be constant.
Right.
Therefore we can say TB by TC would equal PB by PC. So here we have TC equal to PC by PB whole into TB should be equal to this would be PB, this whole into TB.
Right.
This is 1 by 3 PA divided by 2 by 3 PA whole into 850.
Right.
We would get it as 425.
Correct.
Now we use the fact that it is an isochoric process. Now how will we use that is Q equals delta U plus W.
Right.
So since it is an isochoric process, the volume won't change and hence W is 0.
Right.
So the heat lost would be equal to delta U, and we can finally just replace it in CV delta T.
Right.
1 into CV was 3 by 2 R whole into delta T. Delta T is RTC minus TB. So 3 by 2 whole into R whole into 425 minus 850.
Correct.
This would give us minus 5297.6 joules. Since it is negative, hence it was lost.
Right. So we'll move on to the next question now. Let's look at the 13th problem. A vessel of volume V0 contains an ideal gas at pressure P0 and temperature T. The gas is continuously pumped out of this vessel at a constant volume rate R, keeping the temperature constant. Pressure of gas being taken out equals the pressure inside of the vessel. Find the first part of the question is the pressure as a function of time. Prasoon.
So here we see that it is an isothermal process. So we write down a law PV equals nRT, and this temperature always remains constant for the gas in the vessel. Now let's see how the volume, or what is the relationship between the pressure and the volume, the differential relationship. So for that we have PdV plus VdP equal to 0. That is, if a small change in volume or a pressure is made, how they are related to each other.
Right.
So now one thing more is there. This is just a small change, hence it was true. But since the gas is always going out and the remaining is there throughout the vessel,
Right.
so the volume of the remaining gas is always V0. So the volume.
Yeah, so the volume of the gas is basically the volume of the container.
Yeah, volume of gas in the container
Guys, you can make a note of this.
is always V0. This is very important.
That
So-
the volume of the container basically is the volume of the gas. If the volume of the container doesn't change,
Yes.
the volume of the
and-
gas doesn't.
Okay. So we substitute this into a differential equation. We have PdV plus V0 dP equal to 0. So dP by P equals minus dV by V0
Right.
minus dV by V0. So here it is. Now see, this is PdV plus VdP. So we might think because the volume is constant equal to V0, then why are we taking this differential? Why not just put V0 here? It is because we have a particular container, and in that the change in volume is just very small because we are taking out the volume
Right.
in small steps of dV, such that dV by dt in the particular time is equal to R. That is why just a small change is there, but no appreciable change. So this is the differential. Now let's just integrate it. Now before integrating, let's just see that there is a statement here the pressure of the gas being taken out equals the pressure inside of the vessel.
Right.
This is very important because this tells us that the process that is going on is very slow, and inside the pressure is defined, and whatever the change will be, it will be continuous.
Right.
Because suppose if we just take out a whole lot of gas, just say half of the moles we just take out in an instant, then there would not be any equilibrium, and we won't even be able to specify the pressure of this whole gas, because the
Correct.
pressure at every other point would be different.
Right.
So the statement is very important. Now we move on with this. dP by P equals, it was taken out by a particular volume rate R. So basically dV by dt equals R. So this is minus dV, or the change would be R dt divided by V naught. So the limits of pressure we can put from P naught to P, and the limits of time from 0 to T.
Right.
So let's see, ln P by P naught would be equal to minus RT by V naught
Right.
by a simple integration. And so P comes out to be P naught e to the power minus RT by V naught.
Right.
So now let's move on to the next part of this question.
Okay, so the next part of the question asks you about the time taken before half of the original gas is pumped out. How do you do that?
Yeah. So before half of the gas is pumped out, first we see what the N will be. So N is PV by RT.
Right.
So for the particular gas, the volume is the same, so we can write it down as V naught, and the temperature also remains the same. So the only way that N varies is by the pressure.
Right.
So N initial is our P naught V naught by RT, and the final N would be P naught by 2 whole into V naught by RT,
Right.
because that is which will be equal to half of N initial,
Right.
and we directly did P naught by 2 because that is the only way in which the number of moles are varying here, and just by dividing it by 2 we also get half the number of moles. So basically we just substituted into our equation. We had P equals P naught e to the power minus RT by V naught.
Right.
Here our P is P naught by 2 equals P naught e to the power minus RT by V naught.
Right.
From now on it's just simple math. The solving of equation, half equals e to the power minus RT by V naught. So basically the final answer that we get for time would be V naught by R ln 2.
Right. So let's move on to the next question now. Now in question number 14, you're shown a figure which shows a cylindrical tube of cross-section area A. The pistons are connected by metallic wires. Initially, the temperature of the gas is T0. Pressure is P0, which is the atmospheric pressure, PATM. The first part of the question is, what is the tension in the wire? And Prasoon will explain us how.
So this is an easy question. So we just have to do the balancing of forces. So in the starting we see the pressure inside is PATM equals P naught, and here also the pressure is PATM.
Right.
So basically the forces are balanced by the pressure itself, and there is no need for the tension to act.
Okay.
So, or basically writing down the equation, P inside plus tension if it acts would be equal to PATM, since P inside is equal to PATM, P atmosphere, so tension comes out to be 0.
So basically there's no tension in the wire.
Yeah.
Okay, so what will be the tension if the temperature is increased to 2 times T0?
Now let's check this out. P equals nRT by V.
Right.
So initial volume is our okay, we'll see that P initial, which is P naught, was nR T initial T naught by V naught.
Right.
This was the initial pressure in the above question. Now if we increase this or double the temperature, then the pressure would also double. So the pressure would be 2 P naught now, because it's
Right.
directly proportional to T, and volume remains the same.
Yeah, because these are metallic wires, they won't stretch or something.
Yes. So 2 P naught, and P naught was equal to P ATM, so we can write 2 P naught equal to 2 P atmospheric or P ATM. Now we come back to the drawing. Let's draw it again here. Just look at one side of the piston. Here the tension would be acting. From here the P inside would act.
Right.
And here P outside would act, or basically which is the P atmospheric.
Right.
So P outside whole into the area is the force from this side.
Right.
Plus T. So this plus T is the force which is acting on the right hand side. This would be equal to force on the left hand side, because these are like held by wires and they cannot just go away or move. So equal to P internal into area. Tension comes out to be area whole into P inside minus P out.
Right.
Now as we had seen, P inside was 2 P naught and P out was P atmosphere, which was P naught. We get it as A into P naught.
Alright. So on increasing the temperature, we noticed that the tension in the wires was created.
Yes. And I would like to say a few things more. Suppose by any method this inside the temperature could decrease, then these two would move towards each other and like stick together. But because tension cannot act in the opposite direction, this is a metallic wire.
Yeah.
Had a rod been there, in that case it would have provided tension in the outside. And as goes the case for the increasing of temperature, in that case the more we increase the temperature, the more tension will increase.
Alright. So we have found a solution to another problem, and we'll move on to the last problem now.